What if I told you there's an ancient light that fills every corner of the universe, a silent whisper from the dawn of time itself? It's called the cosmic microwave background, and it's not just some faint glow in the void. This is the afterglow of the Big Bang, a fossilized snapshot of the universe when it was just a newborn, barely 380,000 years old. Stretching across the cosmos, this faint radiation holds secrets so profound they could rewrite everything we think we know about reality. And here's the wildest part: despite decades of studying it, scientists are still uncovering mysteries hidden within its shimmering patterns, 25 of them, each more baffling than the last. Picture this: you're staring at a map of the universe's oldest light, a cosmic fingerprint etched into the sky. Every flicker, every subtle variation in temperature tells a story of how galaxies formed, how space itself stretched and evolved, and perhaps even hints of what came before the Big Bang. But the deeper we look, the more questions arise. Why are there strange, unexplained cold spots? Could there be evidence of other universes lurking in the data? And what if the patterns we see aren't just random, but clues to forces we haven't even dreamed of yet? The cosmic microwave background isn't just a relic, it's a puzzle box waiting to be cracked open. This is where the adventure begins. Over the next 25 mysteries, we're going to journey through the most mind-bending enigmas hidden within this ancient light. From anomalies that defy physics to whispers of dimensions beyond our own, each discovery pulls us deeper into the cosmos' greatest unsolved riddles. And the stakes, nothing less than understanding the very fabric of reality. So buckle up, whether you're a seasoned space enthusiast or just curious about the universe's biggest secrets. What lies ahead will challenge everything you thought you knew. The cosmic microwave background isn't just a window into the past, it's a portal to the future of cosmic discovery, and you're about to step through it. One of the most baffling secrets hidden within the cosmic microwave background is something scientists call the horizon problem. Here's what makes it so strange. When we map the temperature of this ancient light across the sky, it's almost perfectly uniform. No matter which direction we look, the variations are incredibly tiny, just a fraction of a degree. That might not sound shocking at first, but think about it. Regions of the universe separated by billions of light years have the exact same temperature, even though, according to the Big Bang model, they should never have had time to exchange heat or information. It's like walking into two different restaurants on opposite sides of the planet and finding them serving identical meals down to the last grain of salt. Only this cosmic version is happening across unimaginable distances. The problem gets even weirder when you realize how the early universe worked. In those first moments, light and heat could only travel so far before the universe cooled enough to let photons roam freely, what we see as the cosmic microwave background today. But here's the catch: the observable universe was already so vast that some regions were too far apart for light to have bridged the gap in time. They were beyond each other's cosmic horizons, forever out of touch. So how did they end up in perfect thermal sync? It's as if someone flipped a switch, coordinating temperatures across space faster than the speed of light should allow. This puzzle led physicists to one of the most radical ideas in cosmology: inflation. The theory suggests that in the tiniest fraction of a second after the Big Bang, the universe didn't just expand, it exploded outward at a rate so mind-bendingly fast that space itself stretched far beyond what light could traverse. Picture blowing up a balloon with a single dot on it. If that dot represents the observable universe before inflation, then in an instant, that dot becomes so small compared to the balloon's surface that any irregularities get smoothed out. That's essentially what inflation might have done: stretched space so rapidly that the entire cosmos became uniform, solving the horizon mystery in one dramatic swoop. But even inflation isn't a perfect answer. For one thing, we still don't know what could have triggered such an extreme expansion, or why it stopped. Some researchers argue that without definitive proof, inflation remains an elegant guess rather than a confirmed solution. Others propose wild alternatives, like a universe that's far older than we think, giving those distant regions more time to even out. The horizon problem is a reminder that sometimes the deeper we dig into the cosmos clues, the more questions we uncover. And somewhere in those faint whispers of microwave light, the truth is waiting to be found. Now, let's turn our attention to something even more perplexing. A cosmic anomaly so bizarre that it sparked debates about parallel universes and cracks in our understanding of space itself. Meet the cold spot, a mysterious patch in the cosmic microwave background that's chillingly out of place. While most of this ancient glow varies by mere fractions of a degree, this region spanning nearly 2 billion light-years is noticeably colder than its surroundings, as if someone left a cosmic refrigerator door ajar in the void. At first glance, you might think it's just a statistical hiccup, a random fluctuation in the data. But here's where things get interesting. The odds of a cold spot this large and this extreme appearing by pure chance are staggeringly low, like rolling the same number on a die 50 times in a row. So if it's not a fluke, what could it be? One leading theory points to a supervoid, an unimaginably vast expanse of space where galaxies and matter are unusually sparse. Picture pouring hot water into a cup with a giant hollow space inside. The heat wouldn't spread evenly, leaving one area cooler. In cosmic terms, if light passes through such a void, it loses energy, appearing colder in our observations. But there's a catch. Even the largest known supervoids can't fully explain the cold spot's extreme temperature drop. That's where the wilder theories come in. Some physicists suggest this could be evidence of a cosmic collision, a bruise left behind when our universe bumped into another bubble universe in the multiverse. Imagine two soap bubbles floating in a sink. Where they graze each other, there's a dimple. If something similar happened on a universe-sized scale, it might have disrupted the fabric of space, leaving behind this eerie cold patch. Others propose even more radical ideas, like exotic physics or defects in the structure of space-time itself, cosmic wrinkles from the universe's earliest moments. Yet, despite years of study, the cold spot refuses to give up its secrets. The more we scrutinize it, the more it defies simple explanations, teetering between a tantalizing clue and a frustrating dead end. Whether it's a window into the multiverse, a flaw in our theories, or something entirely unforeseen, one thing is clear. This icy anomaly is a reminder that the universe still holds surprises we're only beginning to glimpse. And as long as mysteries like this linger in the cosmic background, the story of the cosmos is far from over. If the universe is supposed to be uniform in all directions, no special spots, no cosmic north or south, then why does the cosmic microwave background seem to be whispering about a secret axis? This is the so-called axis of evil, one of the most controversial oddities hidden in the ancient light of the Big Bang. When scientists mapped the tiny temperature fluctuations in the CMB, they expected randomness, a cosmic snowstorm of variations with no particular pattern. Instead, they found something unsettling. Certain hot and cold spots appeared to align along a specific direction, as if the universe had quietly drawn an invisible line through space and arranged itself around it. At first, researchers dismissed it as a statistical quirk. After all, with so much data, flukes can appear significant, but the more we refined our measurements, the stranger it got. The alignment persisted, defying the cosmological principle, the bedrock idea that the universe should look the same in every direction on large scales. Think of it like spinning a globe blindfolded and always landing your finger on the same latitude, no matter how many times you try. If the cosmos is truly isotropic without any preferred direction, then this axis shouldn't exist. And yet there it is, staring back at us from the data. Some theories attempt to explain it away. Could it be an artifact of our solar system's motion, dragging the CMB's light along with it like a boat leaving a wake? Or perhaps contamination from our own galaxy's dust clouding the signal. While these ideas chip away at the mystery, they don't fully erase the anomaly. What's left is far more provocative: the possibility that the universe itself has a subtle directionality, an underlying structure we haven't yet grasped. Then come the radical interpretations. Could this axis hint at something beyond our universe? Some theorists speculate it might be a fingerprint of a pre-Big Bang era, an imprint from a previous cosmic cycle. Others wonder if it's evidence of a larger multiverse, with neighboring universes tugging at ours like invisible magnets. Even Einstein's theory of relativity, the foundation of modern cosmology, assumes isotropy. If the axis of evil is real, it could mean rewriting the textbooks. For now, the debate rages on. Skeptics demand more data while believers search for deeper patterns. Whether it's a measurement error or a cosmic revolution in the making, one thing's certain: the universe has a way of upending our assumptions when we least expect it. And until we solve the riddle of this eerie alignment, the axis of evil remains a tantalizing crack in the mirror of our cosmic understanding. The cosmic microwave background should be a cosmic kaleidoscope, a riot of large and small temperature variations painting the story of the universe's chaotic infancy. But when scientists peered closely at its patterns, they stumbled upon a baffling quietness where there should have been turbulence. The largest scales of the CMB are eerily smooth, missing the dramatic fluctuations predicted by our best cosmological theories. It's like expecting the roaring waves of an ocean and instead finding a pond barely disturbed by a breeze. This absence of large-scale anisotropies isn't just a minor discrepancy, it's a gaping hole in our understanding of how the universe evolved. According to standard models, gravity should have amplified tiny quantum fluctuations from the Big Bang into pronounced wrinkles across space, leaving behind clear imprints in the CMB's temperature map. Yet when we examine the biggest patches of the sky, those expected peaks and valleys are conspicuously muted. Imagine shaking a carpet vigorously, only to find the far corners remain perfectly flat. How could gravity's pull, which sculpted galaxies and clusters with such precision, fail to leave its mark on these vast cosmic canvases? One compelling explanation circles back to inflation, the same theory that tries to solve the horizon problem. Perhaps the universe's hyper-expansion didn't just smooth out temperatures. It might have stretched some primordial fluctuations so thin that they vanished from observable scales entirely. Think of it like zooming in on a digital image until the pixels blur into uniformity. But this raises new questions. If inflation erased these large-scale patterns, why didn't it wipe out the smaller ones too? And why does the cutoff point where fluctuations disappear seem so abrupt, like a cosmic editor snipping away the universe's loudest notes? Then there's the unsettling possibility that we're seeing the limits of our own cosmic horizon. The largest scales in the CMB approach the size of the observable universe itself, meaning we might be glimpsing the edge of what's measurable, a statistical mirage created by our finite vantage point. It's akin to standing in a valley and concluding the entire world is bowl-shaped, simply because you can't see beyond the surrounding mountains. If true, this would imply that the missing anisotropies aren't absent at all. They're just hiding in the unobservable darkness beyond our light cone. Yet some theorists dare to entertain even more radical ideas. Could the universe's surprising smoothness hint at an exotic phase before the Big Bang, a pre-inflationary era that muted the chaos? Or does it suggest that gravity behaves differently on the largest scales, subtly bending the rules we thought were universal? Each hypothesis dances on the knife's edge between groundbreaking and speculative, highlighting how much we still don't understand about the cosmos's grand architecture. The silence of these missing anisotropies speaks volumes. In their absence, we're left with a humbling reminder: the universe owes us neither consistency nor convenience. Every time we think we've mapped its rules, it reveals another layer of mystery, whispering that the story written in the cosmic microwave background is far from complete. And until we crack this cosmic cipher, the quietest corners of the CMB will keep challenging everything we thought we knew. When studying the cosmic microwave background, scientists don't just look at temperature differences. They analyze something called the power spectrum, a mathematical breakdown of how those fluctuations vary across different scales. And right there, in the quadrupole moment, the second largest scale of variation, something unexpected jumps out. It's far weaker than our models predict, as if the universe turned down the volume on one of its most fundamental cosmic harmonies. This anomaly isn't just a minor tweak to the data. It's a glaring discrepancy that could force us to rethink everything from the shape of the universe to the laws governing its birth. To understand why this matters, imagine plucking a guitar string. You'd expect certain resonant frequencies, harmonics, to ring out based on the string's tension and length. The universe works similarly. The quadrupole moment represents one of these cosmic harmonics, a low-frequency note in the symphony of the early universe. But instead of the rich, resonant tone our equations anticipate, we're hearing something faint and muffled like a dampened vibration. The question is why? One camp argues the answer lies closer to home literally. Our solar system's motion through the galaxy creates a subtle Doppler shift in the CMB, potentially skewing the quadrupole measurement. It's like trying to listen to a song while riding a speeding train. The wind rushing past might drown out certain notes, but even after accounting for this effect, the quadrupole deficit stubbornly remains, leaving researchers to consider far more exotic possibilities. Could the universe have an unexpected geometry? The standard model assumes a flat, infinite cosmos, but if space were subtly curved, like the surface of an enormous, gently bending sphere, it might suppress large-scale fluctuations. Picture sound waves traveling across a drumhead. On a perfectly flat surface, they resonate freely, but curve that surface slightly, and certain vibrations dampen out. If the universe isn't as flat as we thought, it could rewrite our entire cosmic playbook. Then there's the tantalizing and controversial idea that the anomaly hints at something primordial. Some theorists suggest an early phase of the universe before inflation might have left behind a kink in space-time, selectively erasing certain fluctuations. Others speculate about relics from a pre-Big Bang era, like echoes of a collapsing parent universe imprinting themselves onto ours. These scenarios flirt with the edges of known physics, but when the data refuses to cooperate, even wild ideas deserve a seat at the table. Yet amidst the speculation, a sobering reality lingers. Sometimes anomalies fade with better data. The quadrupole moment is notoriously tricky to measure accurately, and some argue today's instruments still can't fully separate true cosmic signals from local interference. Future observatories like next-generation space telescopes or ultra-sensitive ground arrays may finally settle the debate, either by confirming the anomaly as a real cosmic mystery or exposing it as a sophisticated measurement glitch. What makes the quadrupole moment anomaly so compelling isn't just its defiance of expectations, but what it represents: a crack in the foundation of our understanding, however small. Whether it points to new physics, hidden geometries, or simply the limits of our tools, it's a reminder that the universe's oldest light still has secrets to spill. And until we crack this code, every whisper from the cosmic microwave background keeps us questioning just how well we truly know the cosmos. Just when scientists thought the quadrupole moment anomaly was puzzling enough, the cosmic microwave background had another twist in store: the octupole moment. This third largest scale of fluctuation in the CMB doesn't just mirror the quadrupole's strange behavior, it aligns with it, as if the universe quietly drew an invisible guideline and decided to follow it. If cosmic randomness were truly random, these patterns should be completely independent, like two dice rolls landing on the same number by pure chance. Yet here they are, eerily synchronized, defying the odds and sending researchers scrambling for explanations. What makes this alignment so unsettling is how it amplifies the mystery of the axis of evil. The quadrupole and octupole moments don't just share a similar weakness, their hot and cold spots seem to know about each other, oriented along the same general direction in space. It's like throwing two handfuls of confetti into the wind and watching them spiral into identical shapes against all probability. For cosmologists, this isn't just a curiosity. It's a direct challenge to the assumption that the universe's structure emerged from chaotic, uncorrelated fluctuations. Some suggest the culprit could be something as mundane as foreground interference. Our galaxy's magnetic fields or interstellar dust might subtly distort the CMB's signal, creating false patterns like reflections on a foggy window. But meticulous attempts to subtract these local effects only deepen the enigma. The alignment persists, stubbornly real. Others propose that the universe's geometry might be playing tricks on us. If space isn't perfectly flat but slightly curved on scales larger than we can observe, it could twist these moments into alignment like a funhouse mirror bending light in unexpected ways. Then there's the spine-tingling possibility that these anomalies are cosmic breadcrumbs, hinting at something far grander. Could the quadrupole-octupole alignment be a fingerprint of a multiverse? In certain theories, neighboring universes in a vast cosmic foam might exert subtle gravitational tugs on ours, imprinting directional biases we can't yet explain. Or perhaps it's a relic from before the Big Bang, a shadow of some primordial asymmetry that survived inflation, woven into the fabric of space-time itself. Yet for all the speculation, one truth remains: anomalies like this force us to question even our most foundational ideas. The universe doesn't owe us simplicity or intuitive patterns. Every time we think we've mapped its rules, it throws another curveball, and in the quiet alignment of these cosmic moments, we're reminded just how much is left to discover. The octupole mystery isn't just a footnote in cosmology, it's a doorway waiting for someone brave enough to turn the handle. The universe is supposed to play fair, no favorite directions, no cosmic favoritism. Yet when scientists split the cosmic microwave background map into northern and southern hemispheres, they found something deeply unsettling. One side of the sky looks subtly but undeniably different from the other. This isn't just a minor statistical blip, it's a full-blown hemispherical asymmetry, where temperature fluctuations in the CMB appear stronger and more pronounced in one half of the universe compared to its mirror opposite. Imagine flipping a coin 1,000,000 times and consistently getting 60% heads. The odds of that happening by chance are practically zero, and yet here we are staring at a cosmic coin toss that refuses to balance. What makes this asymmetry so confounding is how it challenges one of cosmology's most sacred principles: large-scale isotropy. The idea that the universe should appear roughly the same in all directions is baked into nearly every equation we use to describe its evolution. But if matter and energy weren't evenly distributed in the early universe, if one hemisphere cooked at a slightly different temperature, then our foundational assumptions might need a drastic rethink. Think of it like baking a cake where one side rises higher than the other. Something must have disturbed the batter before it set. One leading explanation points to inflation, but not the smooth, uniform kind we usually imagine. Instead, theorists propose a scenario where inflation might have ended slightly earlier in one region of space than another, leaving behind a lopsided distribution of energy. Picture a balloon inflating unevenly, with one side stretching just a fraction more before stopping. That tiny difference could have cascaded into the hemispherical imbalance we observe today. Yet even this elegant idea struggles to explain why the asymmetry aligns so neatly along a single axis, almost as if the universe was deliberately partitioned. Then there's the wild card: primordial magnetic fields. These hypothetical relics from the universe's first moments could have twisted the distribution of matter, creating pockets of density that left uneven imprints in the CMB. It's like stirring a cup of coffee with a magnet inside the swirls wouldn't be perfectly symmetrical. But here's the catch: we've never directly detected such fields, leaving this theory in the realm of tantalizing speculation. Perhaps most provocative of all is the possibility that this asymmetry isn't just a quirk of our observable universe, it could be a window into something beyond. If our cosmos is part of a multiverse, collisions or gravitational tugs from neighboring universes might have tipped the scales, leaving one hemisphere permanently marked. It's a radical idea, but when the data refuses to conform, radical ideas start to look like necessary risks. For now, the mystery lingers unresolved. Every new CMB map adds another piece to the puzzle, yet the big picture remains frustratingly out of focus. Whether it's a flaw in our models, a relic of exotic physics, or a clue to unseen realms, the hemispherical asymmetry stands as a humbling reminder. The universe isn't just stranger than we imagine, it might be stranger than we can imagine. And until we crack this cosmic code, its lopsided whisper will keep pulling us deeper into the unknown. The cosmic microwave background should be littered with colossal rings, ghostly imprints of the universe's earliest sound waves frozen in time. These vast circular patterns, predicted by our best models of cosmic inflation, would be the echoes of primordial ripples bouncing through the newborn cosmos. But when scientists scoured the CMB for these telltale rings, they found something startling. The biggest ones are missing. It's like listening for the deep, resonant boom of a cathedral bell and hearing only faint chimes, a silence where there should be thunder. This absence isn't just a minor gap in the data, it's a potential crack in our understanding of cosmic topology. The largest rings, spanning billions of light years, should have formed when the universe was still a seething plasma, with pressure waves racing outward like ripples in a pond. As the cosmos expanded and cooled, these waves froze into the CMB's temperature patterns, leaving behind concentric fingerprints, their expected size. Roughly 10 degrees across the sky, far larger than most fluctuations we observe. Yet the CMB's actual map shows no such giants. One explanation points to the shape of space itself. If the universe isn't infinite but wraps around in a complex, finite geometry, like a hall of mirrors, it could have snipped off the largest waves before they fully formed. Picture a guitar string, pluck it in an open space and it vibrates freely. Shorten the string and higher notes dominate while deep bass tones vanish. Similarly, a small universe might have stifled its own cosmic echoes, leaving only smaller rings detectable today. But here's the catch: if space is finite, it's far larger than we can observe, making this idea fiendishly hard to prove. Then there's the inflation factor. Most models assume inflation stretched the universe smoothly and uniformly, but what if it didn't? If certain regions expanded faster or slower than others, it could have selectively erased the largest ripples. Think of it like blowing up a balloon with weak spots. Some areas stretch thin while others barely budge, distorting the overall pattern. The problem: such patchy inflation requires exotic physics, like energy fields fluctuating wildly across space, a scenario that's mathematically possible but lacks direct evidence. Or perhaps the answer lies in the primordial plasma itself. The early universe wasn't a perfect fluid. It had viscosity, resistance qualities that might have dampened the largest waves before they could leave an imprint. It's the difference between dropping a pebble into still water and thick syrup. In the latter, the ripples fade before they can grow, but this too raises questions. Why wouldn't smaller fluctuations also be suppressed? The selective disappearance of only the largest rings feels like a cosmic sleight of hand, the most tantalizing possibility. We're seeing the limits of our own cosmic horizon. The largest rings approach the size of the observable universe, meaning their full patterns might extend beyond what we can measure. It's like trying to trace a circle while standing at its center. You'll only ever see a portion of the curve. If true, the missing rings aren't absent. They're just lurking in the unseeable dark, teasing us with their incompleteness. Whatever the cause, the lack of giant rings is more than a puzzle, it's a provocation. Every anomaly in the CMB chips away at our confidence, reminding us that the universe's first light might still be hiding its boldest strokes. Until we solve this cosmic game of hide and seek, the silence of those absent rings will keep echoing through the halls of cosmology, a quiet challenge to look deeper, think stranger, and question even our most cherished assumptions. Among all the enigmas hidden in the cosmic microwave background, few are as unsettling as the dark flow, a ghostly current dragging entire galaxy clusters in the same direction at staggering speeds. Imagine trillions of stars, countless galaxies, all drifting like leaves caught in a cosmic river none of us can see. This isn't just random motion. It's a synchronized march toward something beyond the edges of our observable universe, and it defies everything we thought we knew about cosmic expansion. The discovery came from studying subtle distortions in the CMB. As galaxy clusters move through space, their hot gas scatters photons from the cosmic microwave background, leaving faint imprints called the kinematic Sunyaev-Zeldovich effect. When scientists mapped these distortions, they expected chaos clusters jostling in all directions like commuters in a crowded station. Instead, they found an eerie coherence, hundreds of clusters, some billions of light-years apart, all streaming toward the same patch of sky at velocities exceeding 2 million miles per hour. The odds of this happening by chance, less than 1 in 100,000. What could possibly exert such a titanic pull? The leading explanation, and the one that sends shivers down spines, is that something colossal lurks beyond our cosmic horizon. Not just a supercluster or a void, but a structure so immense its gravity bends space-time across unfathomable distances, tugging on everything within reach. Think of it like standing on a beach, feeling the ocean's tide pull at your feet, even though the water itself is invisible beyond the curve of the Earth. Only in this case, the ocean might be another universe, a supermassive black hole the size of a galaxy, or an exotic concentration of dark matter we've never dreamed of. Skeptics argue it could be a measurement error or an artifact of incomplete data. But after years of scrutiny, the dark flow persists, even in observations from multiple telescopes. Others suggest it might be a remnant of inflation, a lopsided stretch of space-time left over from the universe's first moments. Yet none of these explanations fully account for the sheer scale and coordination of the motion. The most radical possibility, we're seeing the gravitational shadow of another universe brushing against ours. In certain multiverse theories, neighboring bubble universes could nestle close enough to interact faintly through gravity, leaving behind this cosmic wake. It's a breathtaking idea, one that transforms the dark flow from a curiosity into a potential portal, a clue that our universe isn't alone. Until we peer deeper into the void, the dark flow remains a riddle written in the whispers of ancient light. Whether it's a flaw in our models or the first glimpse of something transcendent, one thing's certain: the cosmos still holds tides we're only beginning to sense. And wherever this current leads, it's pulling us toward revelations we can't yet imagine. The cosmic microwave background isn't just a static snapshot, it's subtly stretched and shifted, as if the universe itself is in motion. This phenomenon, known as the dipole anisotropy, was long considered one of the CMB's most straightforward features: a warmer glow in one direction and a cooler shadow in the opposite, created by our solar system's journey through space. Like running through rain and feeling it strike your face harder from the front, we'd expect the CMB to appear slightly warmer in the direction we're moving. But here's where things get weird. The observed dipole is significantly stronger than it should be, up to 10% more intense than calculations predict, as if an invisible hand is tugging us forward faster than the Milky Way's rotation can explain. This mismatch isn't just a rounding error, it's a cosmic speedometer stuck on high. To understand why, picture Earth's motion as a series of nested spins. Our planet orbits the Sun, which orbits the Milky Way's center, which itself drifts toward the gravitational pull of nearby galaxy clusters. Add up all these velocities, and you'd expect a predictable dipole effect in the CMB. Yet the actual temperature difference exceeds these estimates by thousands of kilometers per hour. It's like driving a car with the speedometer reading 60 while the wind rushing past your window screams you're doing 90. Something's off, and the possibilities are as thrilling as they are unsettling. One explanation points to colossal structures beyond our cosmic horizon, mega clusters of galaxies or vast voids exerting gravitational influence we can't directly see. Just as the moon's pull creates Earth's tides, these hidden behemoths might be yanking our entire galactic neighborhood toward them, amplifying our motion. But there's a catch. The scale required would dwarf even the Great Attractor, a known concentration of mass pulling nearby galaxies. We're talking about something so massive it would rewrite our maps of the cosmos. Then there's the darker alternative. What if the dipole anomaly isn't about our motion at all, but a flaw in how we interpret the CMB itself? Some theorists suggest the early universe might have had intrinsic anisotropies, uneven temperatures baked into its fabric before inflation could smooth them out. Imagine a loaf of bread with unevenly distributed yeast. No matter how much it rises, pockets of density remain. If true, this could mean the dipole isn't purely kinematic but carries echoes of a primordial lopsidedness, a cosmic birthmark challenging the assumption of an evenly stretched universe. The most mind-bending hypothesis, the anomaly might hint at pre-Big Bang physics. Certain models propose that our universe inherited its dipole from a parent cosmos, like a spinning top passed from one hand to another. If rotation or other asymmetries existed before inflation, they could have imprinted this peculiar motion onto our newborn universe, leaving us with a dipole that's part relic, part riddle. For now, the discrepancy lingers, a quiet tremor in the data that refuses to fade. Whether it reveals unseen giants in the cosmic dark, cracks in our standard models, or echoes from a time before time, one thing's clear: the universe's motion holds mysteries we're only beginning to unravel. And until we solve them, even the simplest features of the CMB remind us there's always more to the story. The cosmic microwave background is often described as a cosmic fingerprint, a random, Gaussian swirl of hot and cold spots left over from the quantum chaos of the Big Bang. According to our best models, these fluctuations should follow a strict statistical pattern, like snowflakes tumbling from the sky in predictable variations. But what if they don't? That's the heart of the non-Gaussianity debate, a quiet revolution brewing in cosmology, where tiny deviations from this perfect randomness could crack open the door to realities beyond our wildest imagination. At its core, Gaussianity means the CMB's temperature variations should be statistically uniform, with no unexpected spikes or correlations hiding in the data. Think of it like rolling a die millions of times. Over enough throws, each number should appear with equal frequency, and no mysterious patterns should emerge. Yet when scientists comb through the CMB's intricate tapestry, they've spotted faint anomalies, subtle asymmetries, and clustered fluctuations that don't quite fit the Gaussian mold. These aren't glaring errors, they're more like whispers in a crowded room, easy to dismiss as noise until you realize they keep repeating in ways that defy chance. One leading theory blames inflation, but not the smooth, textbook version. Instead, imagine inflation hitting cosmic speed bumps, brief moments where the universe's exponential expansion stuttered or surged. These hiccups could have left behind kinks in spacetime, imprinting non-Gaussian signatures onto the CMB. Picture blowing up a balloon with uneven breaths, some parts stretch smoother than others, leaving behind faint wrinkles. If true, these deviations might reveal the exact physics of inflation, a process so poorly understood it's often called a theory in search of a theory. Then there's the multiverse angle. Some models suggest our universe collided with another bubble universe during inflation, a cosmic fender bender that sent shockwaves rippling through space-time. These collisions could have carved non-Gaussian hotspots into the CMB, like bruises left behind by a primordial crash. It's a breathtaking idea, one that transforms subtle statistical quirks into potential evidence for a reality vaster than we've ever dared to imagine. But skeptics push back. Could these anomalies just be artifacts of foreground interference, dust in our galaxy, or instrumental noise muddying the data? After all, teasing non-Gaussianity from the CMB is like listening for a single off-key note in a symphony. Even tiny errors in calibration or galaxy removal could create false signals. And then there's the curse of a posteriori reasoning. Once you go looking for patterns, it's easy to find them, even where none exist. Without definitive proof, the debate remains a high-stakes game of cosmic clue hunting. What makes this mystery so tantalizing is its stakes. If non-Gaussianity is real, it's not just a tweak to our models. It's a paradigm shift, proof that the universe's birth was messier, wilder, and far richer than we've assumed. Every anomalous fluctuation could be a breadcrumb leading to new physics, from higher dimensions to relics of a pre-Big Bang era. For now, the data keeps us guessing, balancing on the knife's edge between noise and revelation. And until we know for sure, these quiet deviations will keep challenging us to listen harder, because sometimes the universe's softest whispers carry its loudest truths. If the universe were a symphony, then the largest scales of the cosmic microwave background should be its deepest, most resonant notes, powerful vibrations left over from the earliest moments of existence. Yet when scientists measure these vast, slow undulations in the CMB, the music falls strangely silent. The expected power at the largest angular scales is mysteriously muted, as if someone turned down the bass on the cosmos itself. This isn't just a minor technical hiccup, it's a gaping hole in our understanding of how the universe evolved, and it might be hinting at something profound, that our universe isn't infinite, but a finite, closed system with boundaries we can't yet see. To grasp why this matters, picture the early universe as a turbulent ocean, with quantum fluctuations creating ripples of varying sizes. Inflation, the universe's exponential growth spurt, should have stretched these ripples across space, imprinting them onto the CMB as temperature variations. The largest ripples, spanning billions of light years, ought to dominate the cosmic background with their sheer scale. Instead, they're conspicuously faint, like distant thunder failing to rumble. Standard cosmology can't fully explain why these primordial echoes are so quiet, and the discrepancy has sent physicists scrambling for answers. One radical possibility is that the universe is finite but unbounded, a cosmic version of Earth's surface, where traveling far enough in one direction might theoretically bring you back to where you started, just on the other side. In such a scenario, the largest ripples wouldn't have room to fully develop, like ocean waves hitting the walls of a pool. Their energy would dissipate before reaching the scales we'd expect in an infinite cosmos. The math is tantalizing. If the universe's curvature were subtly closed, it could neatly account for the missing power. But here's the catch: our best measurements still suggest the universe is flat to an extraordinary degree, leaving this idea in a frustrating limbo between elegant theory and observable proof. Then there's inflation, or rather, inflation's potential flaws. Most models assume this hyper-expansion happened uniformly, smoothing the cosmos like a perfectly stretched canvas. But what if it didn't? Certain exotic theories propose that inflation might have stuttered or ended patchily, leaving some regions underdeveloped. Imagine blowing up a balloon with weak spots. Those areas would stretch less, potentially suppressing the largest fluctuations. Even wilder are ideas like slow-roll inflation, where the expansion's gradual deceleration could have selectively dampened the biggest waves. These scenarios flirt with untested physics, but when the data refuses to cooperate, even the strangest solutions deserve a hearing. Perhaps the most humbling explanation is that we're simply seeing the limits of our cosmic horizon. The largest scales in the CMB approach the size of the observable universe itself, meaning we might be trying to measure waves so vast they're literally cut off by the edges of what we can see. It's like standing in the center of a vast lake and trying to gauge the full wavelength of ripples that extend beyond the horizon. All we detect are fragments. If true, the missing power isn't absent, it's just lurking in the unobservable dark, taunting us with its incompleteness. But amid these theories, one thing is certain: the silence of the largest scales isn't just a technical puzzle. It's a challenge to our deepest assumptions about space, time, and infinity. Whether it points to a finite cosmos, flawed inflation, or the stark limits of our perception, this cosmic quietude reminds us that the universe still holds mysteries no model has yet cracked. And until we solve it, those missing notes will keep echoing through the halls of cosmology, a haunting reminder of how much we have left to learn. Beneath the smooth veneer of the cosmic microwave background, there might be something even more unsettling than the anomalies we've already uncovered: a spectral fingerprint of so-called phantom dark energy. Unlike ordinary dark energy, which gently pushes the universe apart, this hypothetical variant would wield repulsive gravity so vicious it could eventually rip space-time itself to shreds. And the most alarming part, the CMB might already be showing us its ghostly signature. Dark energy isn't just some abstract idea, it's the dominant force in our universe, making up nearly 70% of its total energy budget. We've long known it's responsible for the accelerating expansion of space, but phantom dark energy takes this to a terrifying extreme. Imagine cosmic acceleration not just as a steady pressure, but as a runaway train with no brakes, a force that grows stronger over time, stretching galaxies apart faster and faster until even atoms can't hold together. The end result, a big rip, where every star, planet, and molecule is torn apart in a final, violent burst of expansion. It sounds like science fiction, but subtle distortions in the CMB's large-scale structure hint that this nightmare scenario might not be purely hypothetical. The clues lie in how dark energy influences the growth of cosmic structures. Ordinary dark energy suppresses the formation of galaxy clusters over time, acting like a gentle counterweight to gravity's pull. But phantom dark energy would do something far more dramatic. It would leave an imprint of accelerated suppression in the CMB's polarization patterns, effectively freezing the universe's structure growth earlier than expected. Recent analyses of data from telescopes like Planck have revealed tantalizing, if faint, hints of this very effect. Anomalies in how gravitational lensing bends the CMB's light that don't quite match standard dark energy models. It's as if the cosmos whispered a warning in a language we're only beginning to decode. Yet proving the existence of phantom dark energy is like trying to catch smoke with your hands. The signal is buried under layers of cosmic noise, and alternative explanations abound. Could it be an artifact of incomplete data, or perhaps an unaccounted-for interaction between dark matter and dark energy? Some theorists even suggest it might point to an entirely new gravitational phenomenon, a crack in Einstein's relativity that only manifests on the largest scales. The stakes couldn't be higher. If phantom energy is real, it doesn't just rewrite our textbooks, it sets a countdown clock on reality itself. For now, the evidence remains tentative, a shadow flickering at the edge of our measurements. But the mere possibility forces us to confront a profound question. Is the universe not just expanding but unspooling toward an inevitable catastrophe? Until we untangle this cosmic riddle, the phantom's whisper will linger in the data, a silent specter waiting to either vanish or rewrite the fate of everything. We think of dark energy as the universe's late blooming rebel, the force that emerged billions of years after the Big Bang to take over and accelerate cosmic expansion. But what if it wasn't a newcomer at all? What if dark energy was there from the very beginning, lurking in the shadows of the universe's first moments? This is the heart of the early dark energy hypothesis, a radical idea suggesting dark energy didn't just arrive fashionably late to the cosmic party. It was there before the decorations were even hung, leaving its fingerprints in the most unexpected place: the polarization patterns of the cosmic microwave background. Polarization is the CMB's hidden language. While temperature maps show us where the early universe was hot or cold, polarization reveals how light was scattered by the primordial plasma, like sunlight glinting off rippling water. And within these delicate swirls, scientists may have found a whisper of dark energy's early debut. The clues lie in something called the E-mode and B-mode polarization signals patterns created by density waves and gravitational waves, respectively. If dark energy was active in the universe's first few 100,000 years, it would have subtly altered how these waves moved through the plasma, tweaking the polarization in ways that don't quite match standard models. Think of it like listening to an old vinyl record. The music, the CMB's temperature fluctuations, plays as expected, but there's a faint crackle in the background, a distortion that shouldn't be there. Early dark energy could be that crackle, a transient phase that briefly flared up during the universe's infancy before vanishing, only to reappear billions of years later. This two-act behavior isn't just speculative. It could solve one of cosmology's nagging inconsistencies, the Hubble tension. That's the growing discrepancy between how fast we measure the universe's expansion today versus predictions based on the CMB. If dark energy had an early burst of activity, it might have tweaked the expansion rate just enough to throw off our calculations, like a sprinter who dashes too fast out of the blocks before settling into a steadier pace. But how could dark energy vanish and reappear? Some theories point to a quintessence field, a dynamic form of dark energy that fluctuates in strength over cosmic history. Picture a pot of water simmering on a stove. Most of the time it's calm, but occasionally a bubble rises to the surface before disappearing again. Early dark energy might work the same way, briefly surging during the universe's fiery youth, then fading into the background until its modern resurgence. The implications are staggering. If confirmed, this would mean dark energy isn't just a passive backdrop to cosmic evolution. It's an active player with chapters in its story we haven't even read yet. And the most tantalizing question of all, was this early phase a one-time event, or could dark energy surge again, rewriting the universe's fate in ways we can't yet predict? The answers might be hiding in those ancient swirls of polarized light, waiting for the next generation of telescopes to decode them. Until then, the early dark energy hypothesis remains a thrilling possibility, one that turns our understanding of cosmic history on its head. Deep within the delicate swirls of the cosmic microwave background's polarization lies a mystery so contentious it split the cosmology community down the middle: the hunt for primordial B-modes. These faint, curling patterns in the CMB's light could be the smoking gun for cosmic inflation, the universe's explosive growth spurt, or they could be nothing more than cosmic mirages, illusions created by dust, galaxies, or even flaws in our telescopes. The stakes couldn't be higher. If real, these signals would rewrite our understanding of the Big Bang. If false, they might expose just how easily we can be fooled by the universe's tricks. The story begins with polarization itself. When light from the CMB scatters off electrons in the early universe, it doesn't just bounce randomly. It gets organized like sunlight glinting off the surface of a lake. Most of this polarization forms what's called E-modes, gentle ripples created by density variations in the primordial plasma, but B-modes are different. These twisted, swirling patterns can only be generated by gravitational waves, the literal ripples in spacetime itself, predicted by Einstein over a century ago. If we could spot primordial B-modes, it would mean we're seeing echoes of inflation's violent birth pangs, the moment spacetime stretched so fast it literally rang like a bell. The controversy erupted in 2014, when a team working with the Bicep 2 telescope at the South Pole announced they'd done just that, detected B modes at a level that seemed to confirm inflation. The scientific community erupted in excitement, but the celebration was short-lived. Further analysis revealed their signal might have been contaminated by cosmic dust in our own galaxy, microscopic particles that can mimic the very patterns researchers were seeking. It was like mistaking a street lamp's glare for the first light of dawn. Since then, the hunt has become a high-stakes game of precision and patience. New experiments like the Simons Observatory and next-generation space telescopes are deploying armies of detectors, each more sensitive than the last, to tease apart the true signal from the noise. The challenge is staggering. Distinguishing inflation's whispers from the cacophony of the cosmos requires measuring temperature differences 1,000,000 times smaller than those your fingertips sense when touching a warm cup of coffee. But the deeper question remains, what if we never find them? Some theorists argue that inflation might have happened at energies too low to produce detectable B modes, or that other exotic physics could have altered their expected signature. Others suggest the lack of a signal might point to something even stranger, alternative theories of the early universe, like a bouncing cosmology or a slow-roll inflation that left no gravitational wave fingerprints behind. For now, the B-mode mystery stands as a humbling reminder of how hard it is to read the universe's oldest messages. Every flicker in the data could be a breakthrough or a blind alley, a cosmic truth or a tantalizing illusion. And until we know for sure, these elusive swirls will keep drawing us deeper into the puzzle, daring us to separate the universe's whispers from its echoes. Among inflation's most spectacular promises was the erasure of magnetic monopoles, exotic, hypothetical particles that should have been as plentiful as stars in the early universe, yet somehow vanished without a trace. These solitary magnets, each harboring just a north or south pole unlike any magnet we've ever seen, aren't just relics of a bygone era. Their absence is a deafening silence in the cosmic microwave background, and it might hold the key to understanding how the universe avoided collapsing under the weight of its own chaos. Picture the primordial universe as a seething cauldron of energy, where forces we now consider separate, electromagnetism, the strong and weak nuclear forces, were once unified into a single, all-encompassing field. As the cosmos cooled, this symmetry shattered like ice cracking across a frozen lake. Theoretical physics insists that such phase transitions should have created topological defects, kinks in spacetime where the fields didn't align cleanly. And magnetic monopoles are the most infamous of these defects, particle-like knots of magnetic flux that should have been produced in staggering numbers, enough to outpace all the matter in the universe today. Yet not a single confirmed monopole has ever been detected. It's as if an entire species of dinosaur left behind towering skeletons, but not one fossil. This is where inflation swoops in as the cosmic cleanup crew. The theory proposes that the universe underwent a period of exponential expansion, stretching space so rapidly that any pre-existing monopoles were diluted to near non-existence, like tossing a handful of sand into an ocean and expecting to find a single grain in every cubic mile. The CMB's eerie smoothness supports this idea. Without inflation's smoothing effect, those monopoles would have tangled the universe's magnetic fields into knots, leaving jagged scars in the cosmic microwave background we'd instantly recognize. Instead, we see a sea of tranquility, suggesting something scrubbed the cosmos clean before the CMB's light was set free, but the plot thickens. If inflation wiped the slate clean, why haven't we spotted even a few rogue monopoles drifting through space? Some theories suggest they're hiding in plain sight, masquerading as heavy, slow-moving particles in cosmic rays, just waiting for a detector sensitive enough to catch them. Others propose they were never produced at all, that the grand unification of forces happened so smoothly, no defects formed. This would mean our understanding of particle physics is incomplete, missing a crucial mechanism that prevented monopoles from ever arising. The most mind-bending possibility: monopoles aren't missing, they're locked away in dimensions we can't perceive. String theory and other frameworks suggest these particles might be tethered to higher dimensional branes, invisible to our three-dimensional tools. It's like searching for a shadow in a room where the light source exists outside your reality. Whether inflation swept them aside, physics conspired to prevent their birth, or they're hiding beyond our perceptual reach, the absence of magnetic monopoles is a gaping hole in our cosmic ledger. And until we solve it, the CMB's pristine silence will keep whispering that the universe's earliest moments were far stranger than we've dared to imagine. The cosmic microwave background spectrum is a relic of such pristine perfection. It might as well have been crafted by celestial hands, a nearly flawless blackbody curve, the kind of thermal radiation you'd expect from an object in perfect equilibrium, spans the sky with a precision that still stuns physicists today. But buried within that perfection are whispers of imperfection, spectral fingerprints that could rewrite the story of the universe's turbulent infancy. Among them, the elusive mu distortion stands out, a hypothetical kink in the CMB's spectrum that might be the only surviving witness to an era of unimaginable violence when the cosmos was less than 300,000 years old. To understand why these distortions matter, picture the early universe as a superheated oven. As it expanded and cooled, photons bounced endlessly off free electrons in a dense plasma, creating a thermal equilibrium so precise that the radiation we observe today aligns almost exactly with a theoretical blackbody curve. But if something disrupted that equilibrium, say, a burst of energy injecting heat into the system, it would leave behind subtle spectral scars. The mu distortion is one such scar, a faint bump in the CMB's spectrum caused by photons colliding with hotter electrons in a process called Compton scattering. It's like finding a single melted tile in an otherwise immaculate mosaic, a clue that something burned here long ago. The hunt for these distortions isn't just academic, it's a window into events too violent to leave any other trace. Take the hypothetical decay of exotic particles in the early universe. If massive, as yet unknown particles evaporated into pure energy during this era, their death throes could have heated the primordial plasma, imprinting a mu distortion detectable today. Even more dramatic are primordial black holes, tiny gravitational monsters that might have evaporated in a blaze of Hawking radiation, dumping energy into the young cosmos like depth charges in a cosmic ocean. These distortions could also reveal the fingerprints of cosmic strings, defects in space-time, left over from the universe's birth, snapping and releasing bursts of energy as they fractured. Yet despite decades of searching, the mu distortion remains tantalizingly out of reach. Current instruments like the Planck satellite have placed tight limits on its existence, but next-generation observatories such as the proposed Pixie mission could finally spot it. The challenge is staggering, detecting a spectral deviation as faint as 1 part in 10 million against the CMB's uniform glow. It's the equivalent of trying to hear a pin drop in a hurricane. What makes this search so thrilling is its stakes. Confirming a mu distortion wouldn't just be a technical triumph. It would be a direct glimpse into a time before atoms, before stars, when the universe was a seething cauldron of raw energy. Every failed detection tightens the noose around exotic theories, while every hint in the data sends theorists scrambling back to their chalkboards. Whether it's evidence of unknown physics or simply proof of the universe's astonishing equilibrium, the CMB's spectral secrets remind us that even the smoothest surfaces can hide the deepest cracks. And somewhere in those imperfections, the cosmos might be hiding its greatest surprises. Hidden within the cosmic microwave background's glow might be the faintest of shadows, ghostly imprints left by particles so elusive they pass through entire planets like they're not even there. These are cosmic neutrinos, and not just any neutrinos, but relics from the universe's first second of existence, racing through space at nearly the speed of light for over 13 billion years. If detected, their whispers in the CMB could crack open a window into an era so remote, Even photons can't remember it, a time when the cosmos was a seething, opaque soup of unimaginable energy. Neutrinos are nature's most aloof particles. Born in the cores of stars and cataclysmic explosions, they barely interact with matter, making them fiendishly difficult to catch. But the oldest neutrinos, those forged in the Big Bang itself, are a different beast. These primordial particles carry so much energy, they're more like cosmic bullets, streaking through the infant universe when it was less than a second old. As they traveled, they should have subtly warped the distribution of matter around them, like a speedboat leaving gentle ripples in its wake. And when the CMB's light was finally set free, those ripples might have frozen into its pattern, leaving behind a neutrino shadow, a barely detectable distortion in the microwave background's temperature and polarization. Spotting this shadow isn't just about adding another trophy to cosmology's case. It's about probing the universe's most extreme conditions, when energies were 1 trillion times hotter than the Large Hadron Collider can replicate. The CMB's photons remember the universe at 380,000 years old, but these neutrinos, they're messengers from the first heartbeat of time, carrying secrets about how the fundamental forces gravity, electromagnetism, the nuclear forces first split apart. If their imprints are real, they could reveal whether these forces unraveled smoothly or in violent, discontinuous leaps, like ice cracking under pressure. The challenge, of course, is separating this signal from the cosmic noise. The neutrino shadow would be buried under layers of interference, galactic dust, gravitational lensing, even quirks in our own detectors. It's like trying to hear a single note in a symphony where every instrument is playing at once. Next-generation telescopes like the Simons Observatory and CMB-S4 are banking on ultra-sensitive polarization measurements to tease it out, hunting for patterns that don't fit the standard models. Some theorists even speculate that these neutrinos could hint at extra dimensions, their path subtly altered by hidden folds in space-time we can't directly perceive. Yet the most tantalizing possibility isn't just confirming these particles exist, it's what they might tell us about the universe's very geometry. If neutrino shadows align in unexpected ways, they could expose hidden anisotropies, cosmic flaws in the fabric of space that contradict our smooth, uniform expectations. Or they might carry traces of collisions between our universe and others in a multiverse, their energies skewed by encounters we can only glimpse indirectly. For now, the neutrino shadow remains just beyond our grasp, a specter hiding in the data. But if we can catch it, we won't just be observing history, we'll be touching a moment older than light itself, a whisper from the universe's first breath. And that's a mystery worth chasing to the edge of the cosmos. Among the wildest ideas in physics is the notion that the universe might be laced with cosmic strings, infinitely thin threads of pure energy, thinner than a proton but stretching across the entire cosmos. These bizarre relics, predicted by string theory, would be like cracks in the foundation of spacetime itself, forged in the fiery chaos of the Big Bang. And if they exist, the cosmic microwave background might be hiding their fingerprints, etched into the ancient light in ways we're only beginning to decipher. Cosmic strings aren't your everyday objects. Imagine spacetime as a frozen lake. As temperatures drop, cracks form in the ice regions where the freezing didn't happen evenly. Cosmic strings would be like those cracks, but on a universe-sized scale, formed when the fundamental forces of nature split apart during the cosmos's infancy. Unlike black holes, which warp space with gravity, strings would bend light through pure topology, creating distinctive lensing effects. And here's where the CMB comes in. As these strings whipped through the primordial plasma, they could have left behind jagged, linear scars in the microwave background, sharp, cold streaks that don't match the usual Gaussian randomness. The hunt for these imprints is like searching for the wake of a boat you've never seen. Scientists have scanned the CMB for telltale signals, sudden temperature jumps along razor-straight lines, or strange patterns in polarization resembling the aftermath of a spacetime earthquake. Some studies claim tentative detections anomalous edges in the data that defy conventional explanations, while others argue these could just be statistical flukes or artifacts of interstellar dust. The challenge is separating a cosmic string's signature from the universe's natural noise, like picking out a single discordant note in a symphony. But why chase such an elusive possibility? Because cosmic strings wouldn't just be curiosities, they'd be evidence that string theory, the famed theory of everything, has a tangible connection to reality. If strings carved their marks into the CMB, they'd offer clues about the universe's energy scales at a trillionth of a second old, a realm no particle accelerator can reach. They might even explain some of the CMB's other anomalies, like the cold spot or missing large-scale fluctuations, by introducing topological defects that twisted the cosmos in ways inflation alone can't account for. The most thrilling possibility is that strings could still be out there today, vibrating like cosmic guitar strings, emitting faint gravitational waves. Future telescopes tuned to these ripples in spacetime might catch their hum, a direct echo of the universe's birth pangs. Until then, the CMB remains our best hope for spotting these ghosts. Whether they're confirmed or debunked, the search itself pushes cosmology to its limits, forcing us to ask, is the universe not just expanding but threaded with scars we've only begun to trace? What if the universe we see around us, the galaxies, stars, even space itself, isn't the deepest layer of reality, but a projection, like a hologram cast from some distant, unimaginable surface? This isn't science fiction, it's a serious, if controversial, theory that might find its most surprising evidence in the cosmic microwave background. The idea, known as the holographic principle, suggests that all the information in our three-dimensional universe could be encoded on a two-dimensional boundary, like a cosmic DVD projecting the illusion of depth. And the CMB's pixel-like fluctuations, those tiny hot and cold spots, might just be the static from that projection, glitches in the cosmic code. At the heart of this theory is a radical rethinking of how information works in the universe. Just as a hologram can store a 3D image on a flat surface, the holographic principle argues that spacetime itself might emerge from a network of quantum bits embedded at its edges. The math behind this comes from black hole physics, where scientists discovered that the entropy, the information content of a black hole, scales with its surface area, not its volume. Extend that idea to the entire cosmos, and you get a universe where the true action happens not in the space we inhabit, but on some distant theoretical shell. The CMB then becomes a kind of cosmic screen, its fluctuations reflecting the quantum noise of that underlying code. The most tantalizing clues lie in the CMB's statistical patterns. In a conventional universe, you'd expect temperature fluctuations to follow Gaussian randomness, no hidden correlations, no unexpected structures. But some researchers claim to have found subtle anomalies in the CMB's data, patterns that resemble the interference you'd see in a low-resolution hologram where information is compressed. It's like zooming in on a digital photo until you see the pixels, except here, the pixels might be Planck scale, the smallest units of spacetime itself. These anomalies are hotly debated. Skeptics argue they're statistical flukes or artifacts of measurement errors, while proponents insist they're the fingerprints of a deeper reality. The implications are staggering. If the holographic principle is correct, it would mean our entire universe is a shadow play, a projection of processes happening in a realm we can't access. Time and space wouldn't be fundamental, they'd be emergent phenomena, illusions created by the interplay of quantum information. Even gravity, the force that shapes galaxies, might be a side effect of this cosmic encoding, a force that leaks into our perceived reality from that distant boundary. But the theory isn't without its paradoxes. If the universe is a hologram, what's projecting it? Is there some unimaginable cosmic hard drive, some ultra-dimensional processor running the simulation? And how do we reconcile this with the smooth, continuous physics we observe every day? Some models suggest the holographic effects would be subtle, visible only at extreme scales or energies, which is why the CMB, the oldest and most pristine light in the universe, might be our best shot at spotting them. For now, the debate rages on. Future CMB experiments with even higher precision could either confirm these anomalies or reveal them as mirages. But whether the holographic principle holds up or not, the mere possibility forces us to confront a profound question. Is reality as we know it just the surface of something far stranger waiting to be decoded? And if so, the CMB isn't just a relic of the past, it's a glitching message from the edge of existence itself. The universe's geometry shouldn't be this perfect. When scientists measured the cosmic microwave background's curvature, they expected some bend, a gentle warp in space-time hinting at whether our cosmos is closed like a sphere, open like a saddle, or flat like a sheet of paper. Instead, they found something shocking. The CMB's light shows zero detectable curvature, as if the universe had been meticulously ironed smooth. This isn't just a lucky coincidence, it's a fine-tuning problem so precise it defies probability. Imagine balancing a pencil on its tip for billions of years. Now scale that up to the entire cosmos. That's the level of inexplicable perfection we're dealing with. At the heart of this mystery lies a number, omega, the density parameter. If omega were exactly 1, the universe would be perfectly flat. Deviate by even a fraction at the Big Bang, and over billions of years of expansion, that tiny imperfection would have ballooned into drastic curvature. Yet measurements from satellites like Planck place omega so close to 1, it's as if someone dialed it in with cosmic precision. The odds of this happening by chance? Astronomical. You'd have better luck throwing a dart across the galaxy and hitting a bullseye blindfolded. This is where inflation swoops in as cosmology's great equalizer. The theory suggests that in the first sliver of a second after the Big Bang, the universe underwent exponential expansion, stretching space so rapidly that any initial curvature was flattened beyond detection, like blowing up a balloon to the size of Earth and watching its surface appear flat to an ant. It's an elegant solution, but here's the catch. Inflation doesn't just predict flatness, it demands it. That raises the unsettling possibility that we're not seeing evidence of inflation so much as assuming it to explain the very flatness we can't otherwise understand. It's like using a magic wand to explain a disappearing act, convenient but hardly conclusive, and the plot thickens. Even if inflation did the job, it leaves us with a deeper question. Why did the universe start so perfectly balanced to begin with? Some theorists turn to the multiverse for answers, suggesting our flat cosmos is just one bubble in an infinite foam of universes, each with different geometries. In this scenario, we lucked out born in a bubble where the numbers lined up just right for galaxies, stars, and eventually, life. Others propose more radical ideas like variable physical constants or gravity weakening over cosmic distances, subtly altering how we perceive curvature. The most humbling possibility, we're being fooled by scale. The observable universe might be a tiny patch of a far grander cosmos with undetectable curvature, like an ant assuming the Earth is flat because it can't see the horizon. Future telescopes mapping the CMB with even finer precision could finally tip the scales, revealing a whisper of curvature or locking in flatness beyond doubt. For now, the CMB's flawless geometry stands as both a triumph and a taunt. It's a cornerstone of modern cosmology, yet it hints at hidden layers of fine-tuning we can't yet explain. Whether it points to inflation, multiverses, or something stranger, one thing's certain: the universe's flatness isn't just a feature, it's a riddle wrapped in the oldest light there is. Buried in the cosmic microwave background's delicate swirls of polarization lies evidence of one of the universe's most dramatic transformations the moment it woke from its dark ages in a blaze of starlight. This was the epoch of reionization, a cosmic dawn when the first stars and galaxies flooded space with ultraviolet radiation, tearing apart the thick fog of neutral hydrogen that had shrouded the cosmos since the Big Bang. The CMB captures this upheaval in a ghostly fingerprint. As those early photons scattered off newly freed electrons, they left behind a telltale polarization pattern, a faint echo of the universe's violent rebirth. But there's a problem. When scientists compare this signal to the timeline of galaxy formation, the numbers don't add up. The CMB suggests reionization kicked off earlier and lasted longer than our best models predict, as if the universe turned on the lights before the stars were fully built. Picture the early cosmos as a vast ocean of hydrogen gas, dark and silent. Then, slowly, the first stars ignite gigantic, short-lived behemoths 100 times more massive than our Sun. Their intense UV radiation begins carving bubbles of ionized gas, like holes punched in a cosmic fog. Over hundreds of millions of years, these bubbles grow and merge until the entire universe is transparent, bathed in starlight. The CMB's polarization should carry the scars of this process, with larger scale patterns reflecting later stages of reionization when bubbles overlapped, and smaller scale patterns encoding the era's messy beginnings. But here's the twist. The data hints that reionization started as early as 250 million years after the Big Bang, long before current simulations show enough galaxies existing to do the job. It's like finding evidence of a forest fire, only to realize there weren't enough trees to fuel it. Theories abound to explain this mismatch. Maybe the first stars weren't the sole culprits. Exotic objects like supermassive black holes or annihilating dark matter particles could have contributed, flooding the cosmos with ionizing radiation before galaxies took shape. Others propose that early stars formed differently than we think, in dense, ultra-efficient clusters that pumped out far more UV light than modern models predict. There's even a wilder possibility that reionization wasn't uniform at all, but patchy and chaotic, with some regions ionizing early while others lagged behind, leaving a distorted imprint that telescopes struggle to interpret. The stakes are high. Reionization didn't just clear the cosmic fog, it set the stage for everything that followed, from the formation of modern galaxies to the chemistry of life itself. If our timeline is wrong, we might be missing a fundamental chapter in the universe's story. Future telescopes, like the James Webb Space Telescope, are hunting for the universe's very first galaxies, hoping to catch them in the act of ionization. Meanwhile, next-generation CMB experiments aim to map the polarization signal with unprecedented precision, searching for clues in the swirling patterns of ancient light. For now, the reionization puzzle remains a humbling reminder. Even the universe's most transformative moments can hide in plain sight, encoded in the faintest whispers of microwaves. And until we solve it, the CMB's polarized light will keep challenging us to rethink how the cosmos emerged from darkness. The cosmic microwave background might be hiding more than just temperature fluctuations. It could contain ghostly whirlpools, remnants of a time when the universe itself flowed like a superfluid. These hypothetical quantum vortices, if real, would be scars from an era before particles, before forces, when spacetime itself behaved like an ultra-cold liquid with zero viscosity, swirling with unseen currents. The idea isn't as far-fetched as it sounds. Under extreme conditions, even the vacuum of space might transition into exotic states of matter, and the CMB's polarization patterns could be our only window into this bizarre, liquid-like infancy. Picture the early universe not as a searing fireball, but as an ultra-dense superfluid, a cosmic analog to helium chilled near absolute zero, where quantum effects dominate and vortices form spontaneously, spinning without friction. In such a state, microscopic twists in spacetime could have stretched to cosmic proportions during inflation, leaving behind telltale spirals in the CMB's polarization. These wouldn't be ordinary swirls, they'd be topological defects, knots of energy where the superfluid's phase wraps around itself like a Möbius strip made of pure spacetime. Detecting them would mean uncovering a hidden chapter of quantum gravity, a regime where the fabric of reality itself rippled with currents we can barely imagine. The hunt for these vortices hinges on their unique imprint on light. As photons from the CMB pass through these spacetime whirlpools, their polarization would twist in characteristic ways, creating spiral patterns called B-modes, but with a signature distinct from those produced by inflation's gravitational waves. It's the difference between tracing the wake of a gentle wave and the violent swirl of a cosmic drain. Telescopes like the Simons Array are scanning the CMB for these anomalies, searching for patterns that defy conventional explanations. Some theorists suggest that if vortices existed, they might also explain other CMB oddities like the cold spot or the axis of evil, as artifacts of spacetime's turbulent past. Yet the challenges are immense. Quantum vortices would be vanishingly rare, their signals drowned out by galactic dust and instrumental noise. Worse still, their predicted signatures overlap with those of other exotic phenomena, from cosmic strings to primordial magnetic fields. Disentangling these possibilities requires precision bordering on the impossible, like listening for a single discordant note in a symphony performed by an orchestra of black holes. But the payoff would rewrite physics. Confirming superfluid vortices in the CMB wouldn't just illuminate the universe's earliest moments. It would bridge quantum mechanics and gravity, offering clues about how spacetime itself emerged from a deeper, more fluid reality. For now, these cosmic whirlpools remain speculative, their existence hovering at the edge of theory and observation. Yet if they're out there, swirling silently in the oldest light we can see, they might be the ultimate evidence that the universe began not with a bang but with a swirl. Among the most electrifying theories in cosmology is the idea that our universe isn't alone, that it's just one bubble in an infinite froth of parallel realities, each with its own laws of physics. But if these other universes exist beyond our cosmic horizon, how could we possibly detect them? The answer might be hiding in the cosmic microwave background, etched into its ancient light like a scar from a long-forgotten collision. Certain anomalies like the infamous cold spot or unexplained alignments in temperature fluctuations could be the bruises left behind when our infant universe bumped into another, a cosmic handshake frozen in time. Picture the multiverse as a bubbling pot of water, with each steam bubble representing a separate universe inflating from its own Big Bang. In this chaotic foam, collisions between neighboring bubbles would be inevitable violent events sending shockwaves rippling through spacetime. If such a collision occurred in our universe's infancy, it wouldn't have just faded into the void. The energy released could have distorted the primordial plasma, leaving behind a distinct signature, a circular imprint of cooler temperatures in the CMB, surrounded by a faint ring of polarization. The cold spot, that eerie 2 billion light-year-wide chill in the microwave sky, fits this description unsettlingly well. It's as if we're staring at the celestial equivalent of a dent in a car fender, evidence of a cosmic fender bender we never saw coming. Skeptics argue that the cold spot could still be a statistical fluke or the shadow of a vast supervoid. But here's where things get compelling. Detailed simulations of bubble universe collisions predict not just cold patches, but specific patterns in the CMB's polarization, subtle, concentric ripples that resemble the aftermath of a pebble dropped into a pond. Recent analyses of Planck satellite data have found tantalizing, if inconclusive, hints of such patterns. Even more provocative are the alignments of low multipole moments, those large-scale fluctuations in the CMB that seem to point in the same direction, as if something outside our universe tugged on the fabric of reality during its birth. The implications are staggering. If these anomalies are indeed multiverse fingerprints, they'd revolutionize our understanding of existence. Suddenly, the constants of nature, The strength of gravity, the mass of an electron, might not be fundamental truths, but local bylaws dictated by our bubble's unique collision history. Even the arrow of time could be a relic of our universe's asymmetrical birth, a scar from the moment we tore free from another reality's gravitational embrace. Yet the debate is far from settled. Without direct observation, multiverse theories risk drifting into untestable speculation. Future CMB experiments like CMB-S4 or next-generation space telescopes aim to hunt for more definitive evidence, searching not just for one cold spot, but for multiple collision scars with matching polarization signatures. Finding even a single confirmed example would open a portal to realms beyond our own, offering a glimpse into the infinite cosmic tapestry lurking just beyond the edges of our perception. For now, the cold spot and its enigmatic cousins remain cosmic Rorschach tests, their true meaning obscured by uncertainty and wonder. Whether they're proof of a multiverse or just statistical ghosts, they remind us that the universe's mysteries often lie not in what we see, but in what those whispers of light refuse to explain. And somewhere in those unexplained patterns, the answer might be waiting, written in the bruises of a collision that shaped reality itself. Right now, the cosmic microwave background glows faintly in every direction, a whisper of heat left over from the universe's fiery birth. But trillions of years from now, this ancient light won't just fade, it will vanish entirely, leaving the cosmos dark and silent in ways we can barely fathom. As the universe expands at an ever-accelerating pace, the wavelengths of these microwaves will stretch until they're longer than the observable universe itself, their energy diluted to near nothingness. The CMB won't just grow dim, it will disappear beyond the edge of detection, like a ship sinking below the horizon of space and time. Future civilizations, if any survive, will gaze into a very different sky. By the time the universe is 100 trillion years old, the CMB's temperature will have cooled to a fraction of a degree above absolute zero, blending into the icy void. Distant galaxies, already racing away faster than light can chase them, will have vanished beyond an impenetrable curtain of darkness. The night sky, once glittering with the afterglow of creation, will be an abyss offering no trace of the Big Bang's echoes. Any astronomers born in that distant era would have no way of knowing the universe had a beginning at all. To them, the cosmos might appear static, eternal, and profoundly lonely. Yet even in its dissolution, the CMB might leave behind one final clue, a ghostly imprint of its own demise. As the last photons redshift into oblivion, they could drag with them traces of the universe's earliest moments, subtle distortions in space-time or relics of quantum fluctuations, frozen like fossils in the expanding dark. Advanced civilizations might uncover these shadows indirectly, through the faint gravitational echoes of inflation or the peculiar motions of stars adrift in an ever-emptier cosmos. It's a haunting thought. The CMB's legacy could outlast its light, lingering as a puzzle only the most ingenious minds could decode. The irony is profound. The very expansion that made the universe habitable, stretching space just enough to allow galaxies, stars, and planets to form, will one day erase the evidence of its own origin. Future scientists might piece together the truth from the thermodynamics of black holes, the slow decay of matter, or the eerie uniformity of a cosmos with no visible edges. But they'll never see what we see now, the universe's first light still shining faintly in the dark, and so the CMB's fate mirrors our own. It emerged in a flash of brilliance, endured for eons as a fading echo, and will one day pass into oblivion, leaving behind only questions written in the fabric of reality itself. The story of the cosmos isn't just about how it began, but how it will be remembered long after its oldest light goes out. From the eerie cold spot to the missing giant rings, from phantom dark energy to whispers of parallel universes, the cosmic microwave background is more than just an ancient glow. It's a cosmic detective story with 25 unsolved mysteries at its heart. Each anomaly we've explored isn't just a gap in our knowledge, it's a crack in the foundation of our understanding, a reminder that the universe is far stranger than we've dared to imagine. Think about it, this faint microwave static, this afterglow of creation, holds secrets that could rewrite physics, redefine time, and even reveal realities beyond our own. And yet, after decades of mapping, measuring, and theorizing, the CMB refuses to give up its deepest truths. Take the axis of evil, a spine of alignment running through the cosmos that shouldn't exist, or the dark flow, dragging galaxies toward some unseen behemoth beyond the edge of the observable universe. These aren't just quirks in the data, they're cosmic puzzles begging for new theories, new tools, and perhaps even new ways of thinking. Even inflation, our best explanation for the universe's flawless flatness, feels like a placeholder, a brilliant idea waiting for proof, or worse, waiting to be overturned. And what about those spectral distortions, those ghostly neutrino shadows, or the holographic whispers hinting that reality itself might be a projection? Every time we think we've got the CMB figured out, it throws another curveball, daring us to look deeper. But here's the beautiful part, these mysteries aren't failures. They're invitations, they're proof that the cosmos still has stories to tell, and that the next revolutionary discovery might be hiding in plain sight, buried in those faint microwave patterns. Maybe the answer lies in a future telescope, a bold new theory, or even a comment from someone watching this right now. That's the thrill of science, it's never finished. So, what's your favorite CMB mystery, the one that keeps you up at night staring at the sky and wondering? Drop it in the comments below, we'd love to geek out with you. And if you're hungry for more deep dives into the cosmos' greatest enigmas, hit subscribe and join us as we keep chasing the universe's biggest questions. Because the CMB isn't just a relic of the past, it's a roadmap to the future, and the adventure is just beginning.